In this chapter, we will be examining a process called confidence intervals as a more sophisticated way of estimating a population proportion or mean. Suppose a researcher is concerned about the proportion of college students who smoke cigarettes. He would like to get a handle on the true proportion of college students who smoke. So one day he interviews 100 students and 23 say that they smoke cigarettes. We know we can't trust a single reading. So what does this sample proportion of 23% say about the true proportion of college students that smoke? How confident can we be that this measurement is close to the truth? In this chapter, we're going to meet confidence intervals, the statistical technique that will answer these questions. Our introduction to confidence intervals is also our introduction to statistical inference, drawing reliable conclusions from data. Confidence intervals are one of the most common tools of inference. They allow us to be precise when someone asks us how sure we are of an answer. What we do know about sample proportions is that they vary from sample to sample, and that when the sample size is large, they are approximately normally distributed. The center of this normal distribution is the true proportion, and the standard deviation of this graph of sample proportions has the formula the square root of p times q divided by n. Now, when we are collecting data on our own, we will not know the value of p, the true proportion which we are trying to estimate. So we'll be forced to use p hat as our best estimate of p. We'll calculate the square root of p hat times q hat divided by n, and use this as our estimate of the standard deviation of the graph of sample proportions. This expression is called the standard error. In our example, where we want to estimate the proportion of college students who smoke, the value of the standard error is 0.0421, or 4.21%. So, given that we had a large sample of 100, sample proportions will be normally distributed. The empirical rule tells us that 95% of sample proportions will lie within 2 standard deviations of the true proportion. Using our 0.0421 as an estimate of the standard deviation, we can see that 2 standard deviations would be 2 times 0.0421, or 0.0842. Now, if we consider 2 standard deviations on either side of 0.23, we find that the interval from 0.1458 to 0.3142 has a 95% chance of capturing the true proportion of college students that smoke. If we convert this to percent notation, we can state with 95% confidence that between 14.58% and 31.42% of college students smoke. So there it is, our first confidence interval. So what is a confidence interval? It's not a single number, but rather a range of values. In this case, the range was from 14.58% to 31.42%. And there is also a statement of how sure we are that our proportion is in that range. In this case, 95% sure. This 95% is called the confidence level. And since we will want to compute many more confidence intervals for proportions, we need to take a step back and review the calculations involved. We started by calculating the standard error, namely the square root of p hat times q hat divided by n. We multiplied this by 2 since we want a 95% confidence interval, and the empirical rule ensures us that 95% of sample proportions are within 2 standard deviations of the true proportion. Finally, we added and subtracted this quantity from p hat to get the range of values within which we expect to find the true proportion of college smokers. There is a special name for the quantity that is added and subtracted from our sample estimate. It is called the margin of error. In our example, it is 0.0842. So, to keep things simple, confidence intervals are constructed by taking the sample estimate and then adding and subtracting the calculated margin of error. Remember that the number 2 that appeared in the margin of error formula was there because we wanted a result we could be 95% confident of. The empirical rule would indicate that if we wanted to be 99.7% confident of capturing the true proportion, we should use the number 3, not 2, to calculate the margin of error. Well, that would make for a larger margin of error. So it seems that if you want to increase your confidence, there's a trade-off. The margin of error gets bigger, and the resulting confidence interval would get wider. Pushing this idea to the limit, if we want to be 100% confident of capturing the true proportion of college students that smoke, our interval becomes so wide that it carries no useful information. So we'll have to balance our desire to be confident with our desire to convey useful information. The 3 most commonly quoted confidence intervals are the 90%, the 95%, and the 99%. Which one you choose depends how important it is that your statement be accurate. In medical research, for example, if you're trying to estimate the percent of patients that will have an adverse reaction to a drug, you may well decide that a 99% interval is appropriate. Information about how likely it is patients will have adverse side effects must be very truthful. In research studies where it's difficult to get a large number of subjects, you will probably decide on a 90 or 95% interval, especially if a ballpark estimate is good enough. In this course, I will always suggest a confidence level for you. So we have almost stated everything that is necessary to compute a confidence interval for a proportion. One detail that remains is the number multiplying the standard error in the margin of error formula. We have seen that it is 2 for 95% confidence and 3 for 99.7% confidence. Well, what about 92% or 98% confidence? What would the number be? Well, its name is the critical value. The secret to finding a critical value is our familiar standard normal curve. We've been using 2 as the critical value for our 95% confidence interval. But if you recall, the empirical rule said that approximately 95% of all observations are within 2 standard deviations of the mean. You may not have focused that much on the word approximate, but now it's time to be a little bit more precise. Using our online Z-calculator, the one at the bottom of the screen, if we select the between option and specify that the shaded area in the middle is to be 0.95 for 95% confidence, the Z-scores that are returned are plus and minus 1.96. Now 1.96 is certainly close to 2, but it's not exactly 2. So from now on, when we want a 95% confidence interval for a proportion, we will use 1.96 as our critical value, not the number 2. All other critical values are simple. To find a 99% confidence interval, we will need the 99% critical value. We'll use the calculator, select between, and specify the shaded area this time as 0.99. The critical value that is displayed is 2.576. For 90%, we do the same thing, and the critical value is 1.645. This slide says it all. It is the all-important formula for computing a confidence interval for a proportion. Write it down somewhere special, and when you get a chance, memorize it.